As an angle changes, its sine and cosine change as a result. We can graph the trig functions by considering the angle theta as the independent variable along the horizontal axis, and the corresponding values of the trig function as the dependent variable along the y-axis. In this video, we'll graph the sine and cosine functions. Here I'm showing a unit circle and a trig functions graph side by side. As you'll see, all the data we plot in the graph on the right comes directly from the unit circle. The horizontal axis of our graph represents the values for angle theta. We usually call the horizontal axis the x-axis, but for now we'll try to remember to call it the theta axis, because each point on the axis represents a possible measure for angle theta. And when graphing trig functions, the theta axis is almost always expressed in radians. When I introduced radians in TR-05 and said engineers, scientists, and mathematicians use radians, I meant in equations and graphs. When measuring angles, such as with a protractor or cutting angles when making something, we use degrees like everyone else, but we use radians with trig equations and graphs. I want to draw your attention to the duality between these graphs. Here's quadrant 1 on the unit circle, and this section of the function graph between 0 and pi over 2 radians represents quadrant 1. I'm color-coding to show the duality. Quadrant 2 includes angles between pi over 2 and pi. And similarly, quadrants 3 and 4 each have their distinct sections of the function graph. As angle theta increases around the unit circle, the value passes through each quadrant. You can see on the right that the independent variable correspondingly moves through all the quadrants. I'm showing and emphasizing only for the range from 0 to 2 pi radians, but of course the graph extends infinitely in both directions. It's always a good idea to start trig graphs with the quadrantal angles, so let's start at angle 0. Its point is on the right edge of the unit circle with coordinates 1, 0. The second number is the sine, so sine angle 0 equals 0. And we'll plot 0 at angle 0 with a red dot. At pi over 2, the coordinates are 0, 1. So sine pi over 2 equals 1. At pi, the coordinates are -1, 0. So sine pi equals 0. At 3 pi over 2, 0, -1. So sine is -1. And at 2 pi, we're back to 1, 0. So sine 2 pi is 0. Well, we might be tempted to connect the dots, but as we'll see, the sine graph doesn't have any straight parts or corners. So let's plot some more common angles. So remember from TR-15 that the sine and cosine for the non-quadrantal common angles will be large, medium, or small. That is, square root of 3 over 2, square root of 2 over 2, or 1/2. Let's start with pi over 4, which is the angle midway between 0 and pi over 2. Sine of pi over 4 equals square root of 2 over 2, which is about 0.707. So since we're just drawing a sketch, we'll estimate about here. Let's go back a bit to pi over 6. The sine of pi over 6 is the small number, 1/2. And at pi over 3, the sine is the large number, square root of 3 over 2, which is about 0.866. And if we sketch it here, that'll be close enough. Due to symmetry about the y-axis, the sine of common angles in quadrant 2 will descend from large to medium to small as theta increases. In quadrant 3 and quadrant 4, the sine is negative, and we can plot out the values of the common angles without too much difficulty. When we connect the points with a smooth curve, we get a shape called a sine wave. For any angle along the theta axis, the graph tells us the angle's sine. The curve oscillates smoothly between -1 and 1. Now let's plot the cosine. Here are the points on the quadrantal angles. Of course, the values will be 1, 0, or -1 at these angles. The cosine curve has the same smooth shape as the sine curve. In fact, it's also called a sine wave, even though it's a cosine. Since the shapes are identical, we just use the term sine wave to describe the shape regardless of the function we're graphing. Once you become familiar with the shape of the sine wave, you can sketch it out from just the quadrantal angle values. Knowing where it's 1 and -1, plus where it crosses the theta axis, is all you really need to sketch the graph. If your instructor tells you to plot some more points, it's easy because we already know the large, medium, and small values for common angles on the unit circle. Of course, for any angle, we can read the sine and cosine directly from the graph. This shouldn't be surprising. We drew the curves to exactly correspond to these function values. Let's look at a few angles of interest. At angles where the curves cross, they have the same value. They cross in quadrant 1 at pi/4 radians, where they both have the medium value, square root of 2/2. And in quadrant 3, they cross at 5 pi/4 radians, where they're both negative medium, negative square root of 2/2. Both functions have the same value at 0 and 2 pi radians, so each cycle begins where it left off, and the curves can continue in both directions. Which curve is sine and which is cosine? One intersects the origin and the other doesn't. If you remember that we think of sine as red and cosine as blue, then picturing a red dot at the origin can remind you that the sine curve passes through the origin, and the blue dot could be up at the top because the sky is blue up there. Of course, you should be able to see the unit circle in your head and know that at the 0 angle, cosine is 1 and sine is 0. You should be able to plot these graphs from scratch. Start with a clean, clearly labeled coordinate system with marked quadrantal angles. For sine and cosine, it's helpful to draw horizontal dashed lines at 1 and -1. Regarding the scale of the axes, remember the trig functions are unitless, so the y-axis doesn't have a unit of scale and is independent from the scale of the theta axis. So the graph's proportions can be whatever is convenient, and you'll often see sine waves compressed like this to show multiple cycles within a given horizontal space. They're still sine waves, no matter how compressed or stretched out they are. There's a lot of graphing-based vocabulary to come in future videos, but I'll start with one term now: period. The period is the horizontal axis distance it takes for the graph to repeat itself, which is the length of the function's cycle. This applies only to graphs that repeat themselves, of course. Not all graphs are periodic, but all of the trig functions are. To determine the period for sine waves, it's convenient to measure peak to peak. Here's what that means. Take a point where the wave is at its maximum, that is 1, then look for the previous value, where it's maximum. The difference or distance between these points is the function's period. For both sine and cosine, the period is 2 pi radians. Notice that we just can't pick a point on a sine wave and then look for the next point having the same value, or we might get an incorrectly short period. So measuring peak to peak or trough to trough is a good technique to identify a function's period. Though it takes 2 pi radians to go completely around a circle, not all trig functions have a period of 2 pi radians, as we'll find out in the next video, TR-19, where we'll graph the tangent and cotangent functions.